Imagine you've just built a brand new large language model, and you want to deploy it as an agent that can use tools, navigate a terminal, and complete real tasks. You quickly discover something frustrating. The model itself is only half the story. The other half is what researchers call the harness, which is all the surrounding machinery, the system prompts, the available tools, the memory, the runtime policies, the verification rules, the recovery procedures, that mediates between the model and the world. And here's the catch. The harness that works beautifully for one model can be mediocre for another, because different models have different quirks, different failure modes, and different sensitivities. So every time a new model drops, human engineers have to roll up their sleeves and handcraft a fresh harness. That doesn't scale. This paper asks a provocative question. What if the agent could improve its own harness? Not with help from a stronger external model, not with a human in the loop, but using only itself, reflecting on its own execution traces. The authors call this self-harness, and they frame it almost philosophically, quoting Bergson on self-creation. Prior work has explored adjacent ideas. Reflection lets an agent store verbal feedback for later attempts. Agentic context engineering evolves the context window over time. MetaHarness uses a stronger external agent to optimize a weaker one's harness. Automated design of agentic systems searches over agent architectures, but all of these either adapt a softer object like memory or context, or they rely on an outside optimizer. Self-harness is narrower and more self-contained. The very same fixed model, operating under its current harness, proposes bounded edits to that harness. The method is an iterative loop with 3 stages. First, weakness mining. The agent runs on a held-in set of tasks and produces execution traces. The failed traces get clustered, but not by surface similarity. Instead, each failure gets a signature with 3 components: the terminal verifier level cause, like a timeout or a missing file, the causal status of the agent's behavior, and the abstract mechanism the trace exposes. 2 failures only end up in the same cluster if they agree on all 3. Think of this like a doctor distinguishing between 2 patients with fevers. The symptom is the same, but the underlying disease is different, and the treatment has to be different too. This careful clustering prevents the system from slapping a generic patch on superficially similar but mechanistically distinct problems. Second, harness proposal. The same model, given the clustered evidence bundle and the editable surfaces of the current harness, is asked to propose several candidate edits in parallel. The key constraints here are diversity across proposals, but minimality within each proposal. Each proposal must target one specific failure mechanism, touch only the harness surface needed, and avoid sweeping rewrites of the control architecture. Each comes packaged with an audit record explaining what it targets, what it changes, and what regression risks it carries. Third, proposal validation. Every candidate harness is re-evaluated on both the held-in split and a held-out split that the proposer never saw. The acceptance rule is conservative. A candidate is promoted only if it doesn't degrade either a split and strictly improves at least one. If several candidates pass, their edits get merged. If none pass, the harness stays the same and the loop continues. This is essentially regression testing borrowed from software engineering, and it's the safeguard that prevents the model from overfitting to its own observed failures. The experiments use Terminal Bench 2.0, a containerized terminal task benchmark with a deliberately minimal starting harness. Just the default deep agent tools, a short system prompt, and the editable interfaces. 3 models from different families are tested: MiniMax M2.5, QN 3.5, 35B, A3B, and GLM-5. The results are striking. On held-out tasks, MiniMax goes from 40.5 to 61.9% pass rate, QN goes from 23.8 to 38.1%, and GLM-5 goes from 42.9 to 57.1%. Quen's relative gain on the held-in set is 138%, and crucially, No promoted harness degrades any split, which is the acceptance rule doing its job. What's really interesting is the qualitative story. The harnesses each model converges on are different. MiniMax learns to create required output files early and to cap unproductive tool use loops. QN learns to pre-check dependencies, break out of exploration cycles, and recover artifacts after tool errors using middleware. GLM5 learns to persist environment changes across shell sessions and to transition more decisively from exploration to implementation. There's a shared theme of artifact reliability across all three, but the specific mechanisms each model needs are genuinely model-specific. Self-harness isn't just bolting on generic best practices. It's diagnosing and treating each model's idiosyncratic pathologies. Now for the limitations the authors themselves flag, and a few they don't quite emphasize. The acceptance gate is just pass-rate non-regression on a fixed benchmark, which means edits could still overfit to terminal bench-style failures. The whole loop depends on having a deterministic verifier that produces clean pass-fail signals, which doesn't exist for many real agent tasks like open-ended writing or research. The edits are bounded, so this isn't open-ended self-improvement. It's more like guided local search through a small space of harness configurations. And there's a subtle circularity. The same model that fails in certain ways is also the proposer trying to diagnose those failures. If the model's blind spots in execution overlap with its blind spots in reasoning about execution, self-harness can't help. Finally, the held-out split is only 64 tasks total split between two splits, so the statistical power behind these gains, while suggestive, isn't overwhelming. Now let's walk through some questions you might have after hearing all of this. First, why does the same model proposing edits to its own harness actually work? Wouldn't you expect it to be blind to its own weaknesses? The trick is that the model is not asked to introspect on its weights or its reasoning. It's given concrete, externalized evidence, clustered execution traces with verifier outcomes, which is essentially a third-person view of its own behavior. Reading your own failed transcript is much easier than predicting in advance that you'll fail. So the proposer is reasoning over evidence, not over self-knowledge, which sidesteps the introspection problem. Second, what stops self-harness from just stuffing the prompt with more and more generic instructions until something sticks? Two things. The diversity but minimality constraint forces each proposal to target one specific mechanism on one specific surface, so you can't propose a sprawling rewrite. And the held-out regression gate means generic, broad instructions that hurt unrelated tasks will get rejected. The qualitative analysis backs this up. The retained edits are small, targeted, and different across models, not bloated prompt walls. Third, what would happen if you ran this for many more iterations? Would performance keep climbing? Probably not indefinitely. The loop is bounded by the editable surfaces of the harness and by the diversity of failure mechanisms still observable after the easy wins are taken. Once the obvious pathologies are patched, the marginal proposal becomes harder to ground in clear evidence, and the regression gate becomes harder to satisfy. You'd likely see diminishing returns and eventually a fixed point where no candidate clears the bar. So how does this connect to large-scale recommendation systems serving hundreds of millions of users? The most direct mapping is to the orchestration layer around LLM-based ranking, query rewriting, or conversational recommendation agents. Production systems running multiple models, say a smaller distilled model for retrieval and a larger one for re-ranking, currently have hand-tuned prompts, tool use policies, and fallback logic per model. Self-harness suggests an automated way to specialize these scaffolds when you swap in a new model checkpoint. You'd run the new model on a held-in slice of replayed user sessions with offline reward signals, cluster the failure modes like hallucinated item attributes or repeated low-diversity recommendations, and let the model propose targeted policy edits gated by held-out replay evaluation. More broadly, the propose evaluate accept loop with strict regression gating is a pattern that recommendation engineers already understand from A/B testing infrastructure. The insight here is to apply that discipline at the level of the agent harness itself, treating prompt and policy edits as auditable, reversible state transitions validated against engagement or business metrics. The key engineering challenge would be replacing the deterministic verifier with noisy offline reward proxies, which would require stronger statistical acceptance tests than the simple non-regression rule used here. But the conceptual blueprint of grounding self-improvement in behavioral evidence, rather than the proposer's plausibility, transfers cleanly.